Some of the most significant breakthroughs in aviation piston engine design occurred between World War I and World War II. Engines like the Daimler-Benz DB601 and the Rolls-Royce Merlin were designed in the early 1930s. Even Radial designs like the Pratt & Whitney R1830 twin wasp, of which over 170,000 units were built, came from that period. Yet, alongside these popular engines were some lesser-known, innovative designs worth taking a closer look at. One such example is the Packard DR-980, and you'd be entirely forgiven if you've never heard of it, as only about 100 were ever built. At the time, however, many considered the Packard Radial to be revolutionary. So, what happened? Why did it fail to gain traction, and what factors led to its failure? In 1927, Captain Lionel Wilson, Packard's chief aeronautical engineer, tested an engine designed by Germany's Hermann Dorner, particularly impressed by its fuel injection system, which allowed combustion of less refined fuels. Building on Dorner's design, Wilson, Dorner and Packard's engineering team developed the DR-980 in the remarkable time span of 1 year, introducing it in 1928. Thanks to Wilson's weight-saving innovations, the engine weighed only 550 pounds or 250 kilograms, challenging the notion that diesel engines were too heavy for aviation. For comparison, the popular at the time Wright J5 gasoline Radial weighed 520 pounds or 236 kilograms and produced similar power at 220 horsepower. With the DR-980 installed in the place of a J5 on a Stinson SM-1, it first flew in September 1928 over Detroit, piloted by Packard's chief test pilot Walter Lees. The oil-burning engine was an immediate hit with crowds and broke several records in the years that followed. In May 1929, Wilson and Lees flew the DR-980 powered SM-1 700 miles from Detroit to Langley Field in Virginia in 6.5 hours, consuming less than $5 worth of furnace oil. In March 1930, they flew the same plane 1,100 miles to Miami, Florida at under 1 cent per mile in fuel cost. The engine soon earned its type certificate, becoming the first certified diesel aircraft engine. The test flights were so successful that Packard commissioned a factory worth $650,000 dedicated to diesel radial production. One notable advantage of the engine was the absence of an ignition system, eliminating electromagnetic interference and allowing clear in-flight radio communications, a major breakthrough at the time. Several more record-breaking flights followed. In May 1931, Walter Lees, flying a DR-980-powered Bellanca pacemaker, set the world record for the longest flight without refueling, staying aloft for 84 hours and 33 minutes. This record stood for almost 55 years. And in February 1932, Ruth Nichols set an altitude record, reaching 19,928 feet in a DR-980-powered Lockheed Vega. The DR-980 was installed in several other aircraft, including the Verville Air Coach, Bull Air Sedan, TAL TA-3 flying boat, and was even offered as an option on the Ford Trimotor, although only one of these were built. Given all these achievements, the DR-980 appeared highly successful. So what went wrong? Why were only 100 built? And why didn't the diesel radial secure a major role in aviation in World War II? Despite its rapid success, the downfall of the DR-980 came almost as quickly. One key issue was diesel fumes. The DR-980 had only one valve per cylinder, handling both intake and exhaust. While the exhaust system routed a lot of the gases away from the cockpit, some of it still managed to escape and contaminate the cockpit, especially when taxiing, before takeoff and after landing, when airflow into the tube wasn't as strong. Ruth Nichols, who set the altitude world record with this engine, reported a strong odor that soaked into her luggage and her clothing, giving off an unpleasant aroma when she made public appearances. While she eventually became accustomed to the fumes, many other pilots strongly disliked flying behind the DR-980, with some outright refusing to fly it. Another major issue was severe engine vibration. Nichols stated that during a record-breaking altitude flight, most of the cockpit instruments broke due to the engine's violent shaking. To address this, Packard reduced compression ratio from 16:1 to 14:1 in 1931. This leads us to the cause of the vibration, which we'll look into in a minute. The sudden death of Packard's chief engineer, Captain Lionel Wilson, further hampered development. On 23 April 1930, Wilson and two associates, flying a DR-980 powered Bull air sedan to an airshow in New York, encountered a snowstorm. An attempt to turn back resulted in the fatal crash. Although the DR-980 program slowed after Wilson's untimely demise, it wasn't halted entirely, so this strategy wasn't the sole reason for the engine's failure. Ironically, the engine's rapid rise also contributed to its downfall. Design began in 1927, the first flight was in 1928, and by 1930 the engine was already on sale. By contrast, the Junkers UMO-205 diesel, which I covered in a previous video, had over 15 years of development. Another development at the time was the increase in aviation gasoline octane ratings, first 87, then 100 octane, which allowed higher compression ratios and improved efficiency. This narrowed the fuel economy advantage of diesel engines. Finally, the onset of the Great Depression surely didn't help. While the diesel engine fuel efficiency might have been appealing during economic hardship, the DR-980 required much more development, an investment Packard couldn't justify at the time. Production of the Packard diesel Radial finally ended in 1933. Let's now examine the engine's design more closely to better understand the technical challenges it faced. The Packard DR-980 was a 9-cylinder, air-cooled 4-stroke diesel radial engine. With a bore of 122 mm and a stroke of 152 mm, it displaced 980 cubic inches or 16 liters and produced 225 horsepower at 1950 rpm. Weighing 250 kilograms, the DR-980 used direct fuel injection, typical for diesel engines, with a compression ratio of 16:1 initially. In terms of performance, the engine delivered 0.25 horsepower per cubic inch and had a power-to-weight ratio of 0.4 horsepower per pound. Its specific fuel consumption was 0.4 pounds per horsepower hour in cruise, notably better than the Wright J5's 0.6 pounds per horsepower hour. The first unique feature of the DR-980 was its diesel cycle design. I've covered diesel aero engines in detail in a previous video, but here's a brief summary. Unlike gasoline engines, diesel engines do not ignite a pre-mixed fuel-air charge with a spark. Instead, they compress only air, significantly heating it. As the piston nears top dead center on the compression stroke, diesel fuel is directly injected into the hot, compressed air, triggering combustion. No spark required. One advantage of this approach is the elimination of detonation risk. Since only air is compressed, premature combustion cannot occur, allowing for very high compression ratios and great fuel efficiency. However, this also introduces challenges. Because combustion begins the moment diesel is injected, the fuel must atomize and mix with the hot air extremely quickly, unlike gasoline engines where fuel and air mix well before entering the cylinder. To ensure precise injection, each DR-980 cylinder had its own combined fuel pump and injector unit. This eliminated the need for high-pressure fuel delivery via tubing, which was prone to failure under the engine's extreme vibration, as well as reducing the risk of vapor lock. The Packard engineers didn't fully anticipate the significant increase in vibration compared to a gasoline radial engine, as shown by the limited countermeasures initially implemented. Radial engines generally have good primary balance, as the crankshaft counterweight opposes the inertial forces of the pistons. With any piston at top dead center, it is 180 degree opposed by the crank counterweight, same when the piston is at bottom dead center. Additionally, the counterweight offsets the rotational imbalance introduced by the mass of the master rod's big end and the articulated rod attachment assembly. However, radial engines inherently have poor secondary balance due to the tilting motion of each connecting rod, causing uneven piston acceleration, a topic I covered in detail in my Radial engine video linked in the description. In the DR-980, vibration was worse than in gasoline radials for two main reasons. First is the heavier reciprocating components designed to handle the much higher combustion forces from the diesel's 16:1 compression ratio. This added mass amplified secondary vibrations. Secondly, maximum cylinder pressures reached over 1500 psi, far exceeding typical gasoline engine pressures of the time. This necessitated additional protection for both the crankshaft and the direct drive propeller. To mitigate transmitted vibrations, the propeller was mounted with a rubber enclosed hub rather than being rigidly attached. On the crankshaft, Packard used spring-mounted pivoting counterweights to absorb combustion shock, instead of fixed weights. Despite these innovations, the measures taken proved insufficient. The DR-980 clearly needed more development time to fully address the vibration problem. One of the most interesting features of the DR-980 was its use of a single valve per cylinder, handling both intake and exhaust. This was one of Wilson's key weight-saving features and also significantly shortened development time, as it avoided the complexity of designing a two-valve cylinder head. However, the design had some drawbacks, most notably that intake and exhaust shared the same path. This not only reduced intake and exhaust efficiency, but also made it impossible to use exhaust pipes. So instead, they came up with an elegantly simple solution by positioning a tube opening into the prop wash or airstream, allowing fresh air to be drawn in by the vacuum created during the intake stroke. During the exhaust stroke, gases were expelled through the same tube, but driven backward by the oncoming air. This setup allowed the use of an exhaust system without requiring intake air to enter through the same path. Early models also lacked a mechanism to throttle intake air. When the pilot reduced the throttle, cutting fuel delivery, the engine continued running on its own lubricating oil, making it hard to land the airplane with the engine still generating power. To address this, Packard introduced air shutters at the front of the intake tubes, which closed when the throttle was pulled back, reducing incoming air and lowering idle RPM. Later models replaced these shutters with a rotating valve that shut off intake air almost fully at idle. Inside the cylinder head, the single valve was offset slightly to induce a swirl in the incoming air, improving fuel atomization. Another benefit of the single valve system was thermal management. Unlike a separate exhaust valve, which typically suffers from heat buildup, the DR-980 single valve was cooled immediately by fresh intake air after the combustion and exhaust phases. The valve train used cam lobes on the cam wheel to actuate rockers via push rods. Being a fuel-injected engine, the cam wheel also included a separate lobe to operate the injectors via push rods, controlling precise injection timing. The DR-980 had several factors working in its favor, which earned it a reputation as revolutionary when it appeared. It produced no radio interference thanks to the absence of an ignition system. It used a safer, more stable fuel, an advantage not lost on airship designers. And it delivered significantly better fuel efficiency, offering both lower operating costs and increased range. But most of these advantages faded in the following decade. Advances in shielding and radio filtering eliminated ignition-related interference on petrol engines. The rise of higher octane aviation gasoline allowed higher compression ratios, improving efficiency and shrinking the diesel advantage. Part of the DR-980's initial success came from Wilson's aggressive weight-saving features, making it only marginally heavier than gasoline rivals. However, solving its major issues by adding a second valve per cylinder, improving counterbalancing and redesigning engine mounts would have added weight, undermining the very property that made the engine attractive. And by the time these improvements could be reliably implemented, aviation gasoline engines had already advanced drastically, driven by the demands of the coming war. One could also argue that the decision to go with a 4-stroke cycle limited the DR-980's potential. as a two-stroke diesel, like the more successful Humo-opposed piston designs that appeared only a few years later, offered inherent advantages in power density, balance, and weight. Though a two-stroke design would likely have required forced induction, offsetting some weight savings, the potential benefits were significant. All these challenges were magnified by the onset of the Great Depression. So, was the DR-980 merely a brief novelty with no real-world application? As the first certified aero diesel, it was a groundbreaking design made possible by Wilson's pioneering weight-saving features, and it served as proof that diesel aircraft engines were not only viable, but had real potential. Its success also spurred aero diesel engine programs by other manufacturers. While it ultimately failed due to limited development and perhaps the missed opportunity to pursue a two-stroke design, the DR-980 deserves recognition for what it achieved at the time. If you're wondering why I haven't mentioned the modern revival attempt by the ZOC Aero Diesel, which addresses most of the DR-980's original flaws, is because there is enough material there to warrant a dedicated video, which will show up here once I've published it. So, what do you think? Was the Packard DR-980 a legend or a lemon? Let me know in the comments. Thanks for watching. See you in the next one.